All right, thanks for that. All right. So we're going to move into 4 more talks on this session before we have a Q&A. So our first speaker of the session is Dr. Vandi, and she got a PhD in robotics from Carnegie Mellon University. And she is the principal engineer and program manager for technology infusion and strategy development at JPL. And the thing I'm most excited about when I read her bio was that she has operated rovers on Mars, the Arctic, Antarctic, and the Atacama Desert. I think that is a really impressive profile. I've never been to any of those places, so that's awesome. And she's going to be talking to us today about some innovations in the robotic search for life. So I'll hand over to you. Thank you.
Thanks, Carly, for the intro. So let me see if I can get this to click. So that is, I'm going to be talking today a little bit, I think, as Carly was mentioned in her talk, which I really enjoyed, was that we've been on Mars for a long time. I think I have to know that this is showing here slower, so that's probably what's online. And we've had a lot of missions, and this is just showing some of the NASA missions that have been there. And I'm going to focus on, have we learned anything from these missions that we could apply to what we want to do in the future? And I was in graduate school when Spirit and Opportunity landed, but they lasted so long that I was able to work on it. And I'm going to focus on some of the missions that I've worked on, which is the rovers, which is Mars exploration rovers, the Spirit and Opportunity rovers, Curiosity, Perseverance, and Ingenuity. In terms of Perseverance, it's been a really successful mission so far, because we learned so much from previous missions. So at the moment, there's actually a science workshop going on about the results from this. And where it is right now at the Crater Rim is a very exciting place. It's collected 26 samples, deposited like 10 of them on the surface of Mars to bring back. And its driving has been largely autonomous. So like over 90% of the driving has been autonomous, and a lot of it is it's covered over 28 kilometers. So we've been able to go a lot of distances. So what is it that you get from robotics is one of the first things I was going to go into. So if you look at this image, when it comes up, it's moving a bit slower, so let me try. Transition. So when it comes up, I'm going to keep clicking and eventually it'll show. So this is the image of Jezero crater. And this is an image taken from orbit. And scientists were really, really excited about it, and they prioritized it. Because if you see in the top left, there is a delta. So there's a delta which is very likely to have signs of ancient life. The black circle shows the landing ellipse. So we've gotten better over time, but even then, it's shrunk, order of magnitude from prior missions, but still it is fairly large. This was 8 kilometers. So the places that we can land on from where we intend are very different. We have never actually ever landed on exactly the spot that we had intended to go. And in the inset, you're seeing images from the Mars Reconnaissance Orbiter high-rise image. And I think it's less clearer, but there's a white path that shows the rover's path. So eventually, when we get to newer planetary bodies and we want to look for signs of life, you want to get to the surface because the mobility allows us to get to multiple locations. And on Mars, we've been to hundreds of locations with Perseverance. And along the way, this is showing images where you can do science investigation. And the hypothesis has evolved. Even though this is such a studied planet, when we landed even with this mission, after a lot of Mars missions, there were assumptions about what we would expect to find. And as it has gone on, you've been able to revise it and make subsequent observations informed by those prior ones. So I think mobility is one of the things that robotics on the surface really gives you. And this, it's one form, driving, but there's a lot of different forms depending on other planetary bodies. And the next one is proximity science. So most of these missions have had an arm that has a whole suite of instruments that you can deploy on the surface. And on the right there, you're seeing one of the instruments that is on the robotic arm, which is an X-ray spectrometer pixel, and the measurements taken by it. That grid there is actually using AI on board. So it takes an image. There is so many ways to adjust the measurements that you make with these science instruments. They're becoming really sophisticated. That it takes an image, looks at the mineral composition, determines what would be more interesting to study carefully, adjusts the position so you make subsequent observations there in real time, so that you're taking the data that is most interesting within millimeters. So this instrument needs to be positioned 2.4 centimeters from the surface to make its measurements. And it's at the end of this very heavy arm, so you have to adjust for it. And the third thing I was going to go into, there's a lot of other factors, but the third main one is the surface of a lot of these planetary bodies, especially Mars, of rocks that are exposed, are very weathered, and you don't expect to find life sitting on the top of the rock, right? Like it's just exposed to radiation, lots of other effects. We expect to find it subsurface, and so having the ability to position an instrument and actually take samples from the surface provides a lot of value. And on the right, so this is the drill, which can take measurements, take intact cores, and on the right you're seeing cross-sections of the cores that it has taken. And this is about the size of a chalk, but you're seeing the variety of samples. So as you're able to get to multiple locations with the robotic vehicle, you can also get a huge diversity of the science measurements. And the science is so much better when you can abrade away the exposed surface, which is usually got a lot of effects from the environment, that you're seeing on the white, the little surface there. This vehicle also has the ability to abrade away the top surface and then place instruments in it. The science return is so much higher that they almost never want to place it just on the bare rock. They want to get under because you can get so much higher valued science. As a result, there's another part that Carolyn was mentioning, is that we're just taking so much data with these instruments, and I think, did it move to the next slide? Let me try again. That we have to also figure out how we're going to take the measurements that actually matter. So this is another capability where you take a wide-angle image with the cameras, and it takes like about 250 targets. And using some predefined criteria based on the scientists, it's determined what are the most interesting rocks where I'm going to get science measurements, because I'm not going to send the data for all 250 of these. So it picked two. And they look rather benign, but it knew based on the measurements that it had made that these would have higher value science. And then there's a SuperCam instrument, which can shoot a laser at the rock and study the plasma with a telescopic lens, and was able to get measurements. So this is one of the rocks where you can make an assumption about, based on looking at it, using onboard AI, what is most interesting, and then send just that data for the most interesting data back to Earth, which really reduces the data volume, but you're actually looking at a lot of targets. So I'm going to go a little bit into how do you make these advances in these technologies in a way, just through one example. And this is autonomous navigation, because it just happens to be something we've tried to do a lot. And this is a big chart, but what it shows is across all the columns are the various missions that have had the ability to drive autonomously. And then there's different forms of it. But the top row is the one that's most interesting, is even Curiosity, which was the most recent mission, had over a decade, has driven far less than Perseverance was able to in just a few years. And so that is a huge leap in capability, which we hadn't been able to make previously. And some of what we get is by doing missions more frequently, which is something, is a challenge, you are able to look at actual data as to where the bottlenecks are. And there may be somewhere where you don't actually expect to actually be able to make the technology advance more quickly. So in this area, one of the things we found was we were able to look at the data, and there's some obvious answers here. The first one is the computing. So actually the rovers, Carly was talking about, or that the compute. Your cell phone has more compute than these rovers still, because it's still using a RAD 750. So that's crazy. And so we looked at the data, and about a third of the processing was being used by just other tasks. So you're driving autonomously, and it doesn't even have the whole CPU, and it's railing the CPU. So this was, for here, the solution was to add a second rad 750, because that's what the mission was willing to do, still relatively risk averse, and then be able to add in FPGA stereo processing that allows you to actually process the data, which is image data, much faster rate. The challenge is that if you just do that and don't actually solve the other problem, the mission can't actually use the technology. So here, there were advances that had to be made in the cameras, because you need to be able to, now that you have faster computing, you can't wait for the mass to move at the slow mechanical speeds to collect the data. The wheels, if they tear up, you're not going to be able to drive over things that aren't a hazard with the compute power you have, but actually tearing up the wheels. So there's a lot of these things that you have data on if you actually do these experiments. And there were other capabilities, like you need to communicate with Earth, and on Mars we have satellites that make it possible, but yet the rover needs to autonomously know where Earth is. And that is something where you have to build in the capability in addition to the other factors. So let me see if it'll move on to the next one. The next one, I just show an image of so this is a video of the actual images from the rover that I use for autonomous navigation. It's sped up, so it takes an image every 1 meter, and sort of is showing you what it is using on board to drive autonomously. But you're still very limited. So there's still a couple of limitations that we're trying to get around for the future. One is just how long you have to drive. So you only get a couple of hours in a day based on the power and the capabilities to do any driving. And the other is you still need human input. And so you can't drive further than 700 over multiple days, meters, because one of the things is that we have been addressing is the rover there's no GPS on Mars, and so it loses track of its position. So as it's driving, it knows that it has no obstacles right in front of it, but it doesn't know where it is on Mars. And so we need Earth in the loop to help it along. And I'm going to go through this a little bit quickly, but here we had another opportunity. So like I said, computing is one of the biggest challenges. Ingenuity was a helicopter that was a tech demo, and tech demos can take more risk. So it actually had the compute that you have on your cell phone. So finally, we're catching up a little bit, and there's a processor that's on the rover that we were like, we can use to actually do some computing for the rover. And we were able to use this to take images. The rover takes a panorama. Currently, what happens is you take a panorama, you send it to Earth, and humans on the ground do the processing and match it and tell the rover where it is and send it back to Mars. Because we weren't able to, before this, do it on board. And this takes a day, at a minimum, maybe more. Now, we can do this on board, and the processor itself can do this in 32 seconds. But the connection between the processor and the Snapdragon is so slow that it takes 17 minutes just to transfer the images. So you can have high compute, but you also have to think of the system as to how you're getting the data into it. And we have to do it twice because it's not radiation hardened. So we reset it and we can compare the results. And so it takes 30 minutes, even though the processing is really fast. So there was another point that I think maybe Carolyn made, which was that, yes, you can believe you can do this, but how do you prove it? And so this is another thing with taking the solving problems where we can do this. So here, we picked this problem to show the ability for the computers because we had a whole data set. Humans had been doing this for a while, and we could show that for every single data set, we can compare and show, and this was, we had a few interns working with us as well on this, is we were able to show that the algorithm can get 100% accuracy with 0 outliers compared to what a human did. This was very compelling, even for a risk-averse mission, because we are using data that they understand, they can see the results, and they can see what your performance is for something that is meaningful. And so this is actually now, we've run it on Mars on the Snapdragon a couple of times, but it's the process of being deployed. And that itself has other challenges I'm not going to go into, with the ground data system needing to be updated to account for these. But it is something where we've been able to take something and put it on a new capability on the mission. So, in the end, I'm just going to spend a few minutes talking about what is the future technology that we need. And this is very challenging because there's a huge leap with what Carly was talking about going into much further out planets. What do we do with robotics? And yes, you'll get 200 answers from 100 scientists. It's the same with roboticists. And so we got 25 participants from 18 institutions, actually some of you are here, to say, let's have a discussion. And this was great because we actually had discussions over several months, and we had scientists and engineers involved to say, let's listen to different opinions. And we started out with hundreds of technologies, but the goal was to come up with just 10, because there isn't enough resources. And could we all, through discussion, come to some agreement? And it had to be things that enable the science priorities. We had scientists in the mix, but we were not going to rewrite what the decadal did. And so it was like, take the decadal, but let's assume they'd be willing to infuse some of these technologies, and how can we enable it? So there was this report done, and there's a few highlights I'm going to go into it. I'm not going to go into all the technologies, but a few things that, as we start to go further out, if we invest in, we would be prepared for this sort of science. So one is to go further and sample more. This picture here is of the South Pole Aitken Basin. So this is the Endurance mission in the Decadal Survey for the Moon. This is one of the largest and oldest impact basins in the solar system. And there's a mission that is going to drive 2,000 kilometers over a period of 2 years. The most we have ever done before is like 20 kilometers in that same time period. So it's a big leap. And then the other one is, it's going to be in very low lighting conditions. So we do need technologies where we can actually do things in the dark, because this is going to be prevalent as we go further out in the solar system as well. And then be able to sample more. So there's a lot of autonomy needed here, autonomous navigation, autonomous mobile manipulation to accomplish a mission like this. The other one was actually quite interesting, and we had a lot of debate about this, is small-scale science robots. So yes, we're increasing the payload, but a lot of these missions are already determined, like Orbilander is a lander, and there's a lot of landers. The potential, the advantage that we get from trial and frequent missions is very high. So if you scale down the robotics, you can add it on smaller scale missions, discoveries and others, and you can also be a secondary payload. And I'm showing examples here of the IRIS rover, which was developed by university students, and it just weighs 2 kilograms. And on the bottom is an actual demonstrated built prototype based on the Ingenuity model that actually has wheels and has a robotic arm, and it weighs 2.6 kilograms. So this can be done. And the question is, we also need to miniaturize the science payloads that they will carry in order for this to actually be useful. And then the last theme that we were looking at is access to extreme terrain and deep under the surface. So these are just examples. So we try to stick to showing images of things that's already been done. This doesn't mean this is the only way. But Carly was showing images of, we want to get subsurface in Europa, but there's kilometers of ice. You might either go through it, you may try to navigate around it. And then also on Mars and other planetary bodies, there is a lot of science to get deep under, and how do we do this? Through lighter platforms that consume less power. So that was another theme that we had. And then, one I'm adding, which was one of the technologies, is the aerial. So, Carolyn talked about the Dragonfly mission. We expect, there's multiple worlds that have atmospheres, and Venus has a lot of interesting science, but it is so hard because there is, whole sulfuric acid layer, and you can't do a lot of remote science observations. So we've been looking at balloons, but there's a lot of interest in also getting to the surface. But there's very few mission concepts that can actually do, for the weight reasons, both of those capable. Oops, it didn't move to the next one. So these are some of the concepts that it talks about as being areas where we can continue to develop the robotics and focus on a few, so that when we do get to those outer planetary bodies, eventually after we have determined what are the most interesting areas, we can actually do in situ science. So that's all I had. So essentially saying that, advances in robotics can help fulfill some of these planetary science goals in the future.
Thank you so much.